So we're going to use the product rule to differentiate this function here, this wave function, with a decaying amplitude, exponential decay, and we're going to find out what the points of maximum and minimum value are by finding these turning points, differentiating it to find a function that tells us the rate of change, finding when that rate of change equals 0, because that's points of turning points, these turning points here. And then once we've found the values for x that give us those turning points, we want to know whether or not it's a maximum or a minimum, so we differentiate again to find the nature of the turning point, and then we substitute our values of x back into the original function to find y. So that's the process we're going to do on this function here, this one. Involves a product rule because t appears twice. So I've got two separate functions involving t multiplied together. So let's do that for this function. This is the rule we've got to use, the product rule, which tells us the differential is u multiplied by the differential of v plus v multiplied by the differential of u. And you remember what we do is we let the first function be u and the second function be v. So we identify what u and v are, and that's normally fairly clear. So we take u and we differentiate it. And we take v and we differentiate it. So the differential of u, using our table of common differentials, bring the power down, multiply by the number in front. So du by dt minus 12e to the minus 3t. That one's easy enough. This one's needs a little bit more thought. As we'll see when we get to these sorts of functions a bit later on, I've actually got a bit more than just a straightforward sine 4x or sine 3x or sine 50 pi t. I've got this 0.4 added onto it. But if you remember our discussion at the beginning about this function, the 0.4 actually just shifts the function left or right. It doesn't have any impact on the gradient of the function. It just shifts the whole function to the left or right. So actually, when we come to differentiate it, we can ignore that 0.4. So ignore that, and then just differentiate the 50 pi t. But a little bit more on that later. So that's what I do when I differentiate this. The differential of v with respect to t. Well, what's the number in front of the t inside the sine function? 50 pi. So that 50 pi comes out. And the sine changes to a cosine. And the rest stays the same, 50 pi t. But the 0.4's got to stay in there. So that's what happens when we differentiate it. So now we can put these values back into this product rule. So the differential of y with respect to x equals u for e to the minus 3t times the differential of v, which is 50 pi cos 50 pi t plus 0.4 plus v, which is sine 50 pi t plus 0.4 plus the differential of u, which is minus 12 e to the minus 3t. So then we simplify and write down this underneath. Just check you can see how this is arrived at. I've multiplied the 50 by the 4, and because this is negative, that makes this negative here, minus 12e to the minus 3t. So we arrive at that. Now, what I'm going to do is to try and remove from the bracket terms that are common. And if you remember, we talked about this last week. It's important because we're going to let this equal 0 in a second to try and find these maximum minimum values. And if it equals 0, I can multiply or divide by anything I like, and that will disappear. So anything that's common to both of these terms is going to end up disappearing. So it's really useful to factorise. Factorise means remove from the bracket what's common to both of these terms. I've got two terms in here, this one and this one. E to the minus 3t is common to both. Pi is not common to both, but I could take out a 2, which is common to the 212. So I could take out 2 e to the minus 3t from a bracket. And then write down what's left inside. What have we got to multiply 2e to the minus 3t by to get back to each of those terms? So just fill in that bracket, and I'll do it in a second. Looking at it again, 4s goes into 200 and 4s goes into 12, so I could take a 4 outside, so try that. So let me just do it then if you're not sure, or let's just check as we go through. So 4 times 50 is 200, so I've got to have a 50 in there. 4 times 50 gives me back to my 200. Pi, I've got to put the pi in, so that will get me back to my 200 pi. Then I've got e to the minus 3t already, so I don't need anything like that in the bracket. But then, of course, it's multiplied by cos of this bracket, 50 pi t plus 0.4. So that's that bit done, right? Okay. There is a case, if you're writing long terms like this, for doing what I did earlier and just, call that something. So because it's not changing at each step, you can do this. But then, of course, in the final step, then put it back in again. So that's that first term done. Now I'm going to look at the second term, so minus, and then again, what have I got to times this by to get me back to that? So this will be, what have I got to times the 4 by? 3 to get back to 12. The e to the minus 3t is there. So all that's left is the sine of that function there. So it looks like that. So I've now differentiated it. And this is my differential function, dy by dt. The rate of change of the original function is given by this. So for any value for t, I could put that into this function and work out what the rate of change of that function is at that point. The gradient, in other words. Yep. So now we've got to let this differential equal 0 to find these points of maximum minimum value and solve it. So we take this function, and hopefully it's the same as we had there. Oh, I didn't take the 4 out, so I did that. Don't know why I didn't do that. So let's take the 4 outside now, or 4 e to the minus 3t 50 pi cos the bracket minus 3 sine the bracket equals 0. Might as well take that 4 outside as well, mightn't we? So now comes the bit that's going to make things a bit easy for us. Because this is 0, I can divide or multiply this side by anything I like, and it'll always be 0. So why not divide this by 4 times e to the minus 3t? Because if I divide this side by 4e to the minus 3t, it goes. So divide both sides by 4e to the minus 3t, and that will disappear. So this implies that dividing both sides by 4e to the minus 3t, 50 pi cos of this bracket minus 3 sine of this bracket equals 0. The 4e to the minus 3t term disappears. Now what I'm going to do is use a little fact that I remember, and that's this. Tangent of the bracket is the sine of the bracket over the cosine. Tangent is sine over cosine. And when we looked at, when we look more at wave functions, we can see that little identity maybe come out. So the tangent is sine over cosine. So I can actually manipulate this. So I've got sine over cosine. I'm going to take this 3 sine bracket over here and then divide both sides by the cosine to get sine over cosine. So looking at this line here, this one, oops. So if we take that line above 50 pi cos bracket, equals 3 sine of the bracket. Adding 3 sine bracket to both sides, I get that. What I'm after here is getting t. I want to get t on its own so I can work out what value of t gives me 0, in other words, a maximum or a minimum. So solving for t, which is inside this bracket. So at some point, we're going to have to put that bracket back in again. So I know that sine over cosine is tangent, so let's divide both sides by cos of the bracket. So 50 pi equals 3 sine of the bracket over cosine of the bracket. Taking the 3 over to the left-hand side, 50 pi over 3 equals the tangent of the bracket. So you've got a tangent button on your calculator, and what I'm after is, now let's put this bracket back in again. 50 pi over 3 is the tangent of 50 pi t, because that's what we had originally, plus 0.4. That was what the bracket was, wasn't it? So we've got to put that back in again now, because we want t. We want to get t. So we actually want the angle whose tangent is 50 pi to get this. So the bracket 50 pi t plus 0.4 is the angle whose tangent is tan to the minus 1, in other words, of 50 pi over 3. So 50 pi t plus 0.4 equals, yeah, we want it in radians. It is in radians. .55. So now we can find t. We can subtract 0.4 from both sides and divide by 50 pi. So 50 pi t is 1.15, subtracting 0.4 from both sides. Oops, t. So t equals 1.15 over 50 pi. So we can work out what that is. So to one significant figure, 0.01 seconds is the time we get our first maximum value. So if we look back at the function, that's 0.1 seconds here. So 0.01 seconds there. And if I were to zoom in on this function using autograph, I'd find that my first maximum occurred at 0.01. At this stage, I don't know whether it's a maximum or a minimum. I mean, if I've plotted it, I know it's a maximum. But what I can do now is I can say, okay, if the time is 0.01, then what's the value of this function at that point? And I can plug it into here, let t equal 0.01, and put this in, and I'll have the value of y at that point. So we're on our way with this thing. A word on this tangent function. Here is the tangent function underneath here. So what we're saying is that at the moment we have t equal to 0.01. The tangent is 50 pi over 3, whatever that is, 50 pi over 3. So we've got some value here, 50 pi over 3, and that's our value here that we've got. And if you look at it, this is a repetitive function, the tangent function. If I, let's look at this function for a second. If I draw a little right angle triangle here, that's my angle theta. And if you remember, this is taken from a rotating vector, rotating anticlockwise, around like this. Oops. Okay. And so as time goes by, this vector here is going to go from 0, so it starts at 0, 0 here, and then the tangent of the angle is the opposite over the adjacent. So as this thing rotates around here, the opposite is going to get bigger and bigger and bigger, and the adjacent is going to get smaller and smaller. If I have it over here somewhere, the right angle triangle can be like that. So this is going to approach 1 at the top, because the length of this vector is 1, and this is going to approach 0. So at 90 degrees, it's going to be 1 over 0, and anything over 0 is infinite. So at 90 degrees, or if this is in radians, what's 90 degrees in radians? Sorry, 0.5 pi, right, pi over 2. At pi over 2, this thing's going to shoot off to infinity. So that's why the tangent curve looks like that. And then it rotates all the way around and repeats. So pi later, half a turn later, we're going to repeat. We're going to have the exact same thing happening. Pi, so pi over 2, it's here. It's here. And then pi later from that, which is back round here again, so that's pi later. We've got another situation which shoots off to infinity. So it repeats. And we can say, if I've got this here, this time here, then it's going to repeat this period of time later. And if you look at the difference between here and here, it's 3.142, in other words, pi. So if I've got my time of 0.01, that's this one here, if I add pi to it, I'll have the next time it drops to 0, the gradient, and so on. So if I keep adding pi, I'll get more and more times that I get a maximum or a minimum. So, and that's why I get a series of maximums and minimums appearing in this function. It's every pi that it works. So, back to our solution. T equals 0.01 is our time, and then if we wanted successive ones, we could add pi, and we could get further times that this will drop to 0. What I want to do now, though, is just determine whether or not this is a maximum or minimum, so I need to differentiate again. I need to take this function and differentiate again. I've got t appearing here, t appearing here, and t appearing here inside this bracket. So actually quite an involved process. So I'm not going to do it, okay? But that's what we do. The second differential is positive, we've got a minimum. If it's negative, we have a maximum. I think we sort of mentioned this little memory aid thing here before, didn't we, last week? Okay? So if we really needed to determine whether or not this was a maximum or a minimum, we could find a second differential. And then for step 4, we'd put our value back in for t into the original function. Y equals 4e to the minus sine 50 pi t plus 0.04. Obviously I used the value 0.007, rounded to 0.007 when I looked at this. And that would give me a value of y equals 3.91. Just to finish this little step off, just check that you can do that. So put that value of t, 0.07, back into that function and check you get 3.91. Try and do it in one hit on the calculator.